Now, for more advanced features, we are going to be demonstrating the PID controller. The PID configuration page is a page in NRConsole that displays all of the information for setting up and running the Neuron Robotics PID controller. Inside the DyIO, you have 8 PID groups 0 through 7. We will be using 2 of them today. And you can select from any group to do configurations with. To start with, you select which DyIO channels you want to participate in this PID controller. For more information on what a PID controller is and what math governs it, please see the attached link. The first stage is to select an input. For our purposes, we're going to be using the Neuron Robotics Quadrature encoder, as demonstrated by our Ackerman Steer robot. As mentioned earlier, we have 4 quadrature encoder channels. We're going to start with the channel that is on channel 22 and 23. You plug one of the quadrature encoder channel signal wires into 23, and you plug the other one into 22. Now, to use the servo motor, we're going to have to set the other channel bank from sensors to motors, and use our adapter cable with a standard RC battery or battery pack. Now you'll notice that the LED on the bank that is set to motors has gone from an orange to red. You'll also notice that NRConsole notifies you that the battery has been connected. Now we can begin configuring our PID controller. Our input is going to be channel 23. Our output is going to be channel 11. If you start your PID controller and notice your motor begins moving immediately, you can first of all stop all PID controllers, go back to the DyIO panel, and make a configuration to this channel. What we'll notice here is that this device, this particular servo, stops on value 124. To let the PID controller know that that is where stop is, we set it as the default value. Now we come back to the PID controller and continue configuring. We'll set a proportional gain of 1, an integral gain of 0, and a derivative gain of 0. For more advanced users, you can begin to get better control loops by altering these values. And we're going to hit Configure PID Controller. Now, to test the controller, we'll give it a set point. 100. You'll notice that the PID controller is what's called divergent. The set point went up, but the motor sent the value spiraling downwards. There's a configuration for this, and this is what's called the invert control. Check the checkbox and configure your DyIO again. and try setting a new set point. You'll notice now that the controller is convergent. The other mode you can use the PID controller for is with an analog input and a servo output. For this one, we're going to set channel 12 to analog input and then plug in our analog sensor. Note, signal always goes closest to the bowler hat, and we can observe on the screen the analog value moving. We'll plug the motor in to channel 10 and set channel 10 to be a servo output. Since this particular servo seems to have 128 as its stop point, we're going to set that as the default. Head over to the PID controller and select a new control group. You'll notice this group has all of its configurations set back to default since it hasn't been used yet. For the input, we'll select channel 12, and for the output, we'll select channel 10. Configure the DyIO channels, set the gain to 1, and configure the DyIO. What we want to check with the analog, since it can't spin continuously, is to see if the system is diverging to begin with. So what we'll do is move the sensor and notice that the servo is driving the sensor further away from convergence. This means that this system, like the other one, will also need to be inverted. We check the invert box and reconfigure. Now we notice the motor is always driving to convergence, and we slide the gear down to engage the controller. And we can set points. Settles roughly around 100. Set it to 1,000, and it'll settle at 1,000. You'll notice that this is an active controller, so if I come in and disturb it, it will not only fight back, but correct itself. And that is the Neuron Robotics PID controller. It should be noted that the PID controller is running entirely inside the DyIO module. This means that all of the control loops are running real time. What that means is inputs are calculated right on the DyIO controller, and outputs are set directly from commands inside the DyIO. That means no data has to be sent up to the computer to be processed to run the PID controller. This means your PID controller can run much faster than your communication speed. The communication speed for the DyIO is anywhere between 6 and 35 milliseconds depending on the size of the packet that you're sending. However, internally to the device, you have a 1 millisecond control loop running your PID controller.